Good afternoon, everybody. When I got into this hotel, I was wondering, what is this black sheep in the fawn coat doing in a very large gathering of industrialists and other eminent people, and also people here largely talk about AI, ML, large language models, big data, and so on. Did I come to a wrong place, or did they call the wrong person? I also thought for a minute, my son also, he works for our friend, and when I got in, he was sitting on the dais. I thought he also publishes by the same name, yes, Asokan, and I thought whether they called me instead of him. This happens very frequently. I get emails and my emails go to him. So then I realized maybe this is not the case. And then there may be some connection because ELCIA wanted to set up a center for excellence in sensors shortly. So that may be the real reason for having me here. And also when Vaidi called me, he gave a very fancy title, Sensor Blueprint. So I told him when I called him a few days back, I said, it's difficult to talk about a blueprint in 15 minutes. And that too, sensor is a huge area, This is like talking about Indian history in 15 minutes. So I said, no, I would hesitate to do so. But let me give some brief, presentation about some greener pastures instead of, blueprints. So what are some new emerging technologies in the area of sensors? And I thought when we talk about emerging technologies in the area of sensors, will they be adaptable from the Indian perspective? Can we use them, or can we bring it to the market? So I thought that will be more relevant for ELCIA. And then I thought, okay, let me pick up one particular topic, namely fiber optic sensors, which have vast applications, versatile sensors, I would like to call them, and vast applications. So I would illustrate this in few minutes time, and this is about me, and then this is about what Paul Jacobs told long time back. Now the world has become more automated than ever before. So all our life is automated, and our cooking is automated, our driving is automated, whatnot. Our living has become automated. Soon our breathing also will become automated. So when we talk about a connected world or cyber physical systems, even human beings have become cyber physical systems. So when we have a CPS system, the heart of CPS is sensors. In this rabbit here diagram, initially I used to have this rabbit here diagram with all 3 ears with communication, computation, and sensors and actuation. Then I thought, okay, let me have some more justification for my stay and called sensors are the heart of any CPS system. Okay, so when we talk about sensors are not new to humans. Our body has so many sensory systems. We have talked about electrical, mechanical, electromechanical, chemical, and so on. Optical sensors are fairly, more recent in the chronology, and then, and they work on the principle of, interaction of light with matter. So they come with very different types: interferometric sensors, colorimetric sensors, spectroscopic sensors, resonance-based, absorption, transmission, refraction, diffraction, you name it, whatever. There are several types of physical phenomena are routinely used. So again, when we talk about sensors, and let me also give you a very brief idea about what type of market we are looking at for sensors, globally, Asia-wise, and also international-wise. So this is for Vaidi, because he said I should have some slide on numbers. Okay. So if you look at the real market share, so the sensor market is growing annually in a very rapid phase, and then you see that it is significantly reaching about $450 billion by the year 2030 to 2035. So Asia Pacific alone is contributing to about 40% of the global market share. This is valued about 80 to 90 billion dollars in 2021 with about 9% CAGR through 2029. So obviously China is a leader. It contributes to a very large extent in this segment and dominating in areas like consumer electronics, EVs, smart cities and so on, followed by Japan and South Korea. And I deliberately didn't want to put the numbers of India because we wanted to go to the top place in Asia Pacific in the next 10 years. So if you look at the year-on-year growth, the sensor market grows steadily, again about 8 to 9%, 10% growth. And the market, as I said, by 2022, it's about 450 billion US dollars it is going to reach. So when we talk about optical sensor, let me concentrate on a particular type of optical sensor, which is a low-hanging fruit. When I say low-hanging fruit, I'm not talking about the technology is low. Why I would like to call it as a low-hanging fruit is, we have a communication industry which is very mature. We have fiber optics, which is highly advanced stage because of the communication industry. And if I look at any component which is needed for the sensor, fiber optic sensor industry, they are all there, be it source, detector, waveguide, circulators, direction couplers, all of them are being made for the communication industry. We don't need to reinvent anything for the sensing industry. We can happily piggyback on the optical communication industry, and then we can contribute to this optical sensing industry. And optical sensors have very many advantages compared to mechanical or electrical sensors. The best or the most important being immunity to electromagnetic interference. So whenever we have electrical sensors, especially in a strategic application like defense or aerospace, EMI can cause a big problem. Noise floor is very high, and therefore if you have a pickup, then this can cause havoc to your measurement. And optical sensors are basically intrinsically immune to EMI. They are very sensitive, and if you look at the conventional electrical sensors, optical sensors in many cases, orders of magnitude better in terms of sensitivity. Small footprint. If you look at a fiber optic sensor, we are talking about a diameter of an optical fiber which is about 125 micron in diameter. So the footprint is very, very small. Chemical and electrical passiveness. Silica, made of silica, it is chemically passive. You can use in any corrosive environment. Nothing is going to happen. And secondly, it is electrically passive, especially if you are going to use for biomedical application. Electrical passiveness will be a very important aspect there. Multiplexing capability. Fiber optic sensors can be multiplexed. You can put 200 sensors, 300 sensors in one optical fiber. And you will have the optical fiber which is functioning as a sensing element as well as the communication element. Both the purposes are solved, and the sensed data can be taken to kilometers far away without any attenuation. So you have a long distance sensing communication possibility which is packaged into one. So this is a very important advantage. Long-term stability. Optical sensors are stable for decades. So again, if I come quickly to the market share, see the fiber optics sensor market share is about 4 million US dollars, 4 billion US dollars in 2024. And then Asia Pacific, again led by China, and then again Japan comes behind, South Korea and India and so on. So again, if you look at the market, which is going to evolve in the next 10 years by about 10%. So if for the industry, particularly the Bangalore Electronic City industries, there is a large potential to get into optical sensing. So our sensor incubation center or the acceleration center which you are talking about in the months to come, I told it is getting funded by the state government, and MIT is also going to fund. So we are going to have a large, preferably a large impact in this area, so that we would be able to bring to the market what is being conceived in the lab and then what can be manufactured and then sold in India. So if I come to the application domains, you name it, all of them are there. Industrial automation, manufacturing, civil engineering, biomedical, defense, environmental, everywhere there is potential application of fiber optic sensors. So this can be a very, very important thing. So with this about some brief thing, I also would like to beat self-drum. So I will also talk about my own work because it's passionate. I have been working in the last 2 decades in optical sensors. So I would like to tell about what I have been doing very briefly and some of our contributions. So I work in a sensor called fiber Bragg grating. So I usually begin my talks with a song from Sound of Music. If you know Do Re Mi, you can almost sing anything. So similarly, if you have a fiber Bragg grating, you can sense almost anything. This is perhaps one sensor which is known to us, which can be a physical sensor, which can be a chemical sensor, which can be a mechanical sensor, which can be a biochemical sensor, and so on, the way how you configure and how you use. Let me start with what is a fiber Bragg grating. Let me take few minutes, and then a fiber Bragg grating, we all know about optical fibers. It has a core which is about 8 to 10 micron in diameter, which we have a clad which is about 125 micron in diameter. Leave the polymer sheath outside, which is for strength and then ruggedness and so on. So our high school physics says the core refractive index is slightly higher than the clad refractive index. So when I launch light, it goes through unattenuated, and what we put on the left hand side comes on right hand side kilometers away. But if you look at a normal single mode optical fiber, we have the core refractive index is uniform all along the core, axially. But if I want to make it, this is about communication. Our Kumar Shivarajan is happy with an optical fiber with an uniform refractive index core. But I am not happy because I want to play with it to make it into a sensor. Well, how do I do? I change the uniform refractive index of the core into a sinusoidally varying refractive index. If I have to give a rough analogy, a normal optical fiber is like an uncut bread loaf, unsliced bread loaf. Whereas a Bragg grating, fiber with a Bragg grating is an optical fiber in which a bread loaf is sliced. It is analogous to a bread loaf which is sliced. So we have regions of varying refractive index. So if you look at the view graph here, so if you look at this is the normal optical fiber. All along the fiber there is uniform refractive index, whereas in a fiber Bragg grating we have slices where the refractive index varies. So this is like N1 plus or minus delta N1, N1 plus or minus delta N1 and so on. So what do we have? When I have a grating written on an optical fiber, if I put light into an optical fiber, in a normal optical fiber, what you put on the left side comes on the right side, unattenuated. But with a fiber with a grating, what happens is one particular wavelength is reflected back and the remaining wavelengths are transmitted. So the reflected wavelength, which I call as a Bragg wavelength, which is a very sensitive function of the pitch of the grating, which is called the distance between two refractive index modulation, which I call the pitch, and the effective refractive index, which depends on the core and the clad refractive index. So if I want to use a fiber grating as a sensor, I either play with the change in the pitch or change in the refractive index to measure something. So let me put this video. Can I please play the video, please? So this shows about the technology. This is optical fiber. I photo imprint refractive index modulation in the core. Once I do that, so we have got the refractive index modulations built in along the axis of the fiber. Then when I launch light, you see I launch a broadband light containing all wavelengths from the left to right. One particular wavelength is reflected back, which I call the Bragg wavelength, and the remaining wavelengths are transmitted. So when I pull the fiber, for example, the pitch changes. Once the pitch changes, the wavelength shifts. So I can use the shift in the wavelength to very precisely measure the tension which is imparted on the fiber. So the most conventional application is bound to a structure. When the structure deforms, when there is a tensile strain or a compressive strain on the structure, the wavelength shifts I can very precisely measure. Or I can heat. Once I heat again, the pitch changes, I can measure. So if you look at if I look at the FBG, in a native form, a fiber Bragg grating measures strain and temperature. But with suitable transduction, I can measure acceleration, I can measure displacement, I can measure vibration, I can measure any parameter by playing with the change in the pitch. By playing with the change in the effective refractive index, I can measure chemical concentration, I can measure biological, cardiac vascular marker concentration, I can measure proteins, very many applications are possible. So with this, I will give you one or two simple examples of the applications. Traditionally, the application of fiber sensors have been in structural health monitoring. You bond to your structure and measure the strain, temperature, vibration, displacement, and so on. So if you look in China, most of their bridges are instrumented. They are provided with structural health monitoring sensors. Our country, there is no regulation, there is no mandatory requirement, so nobody instruments. But nevertheless, this market is going to arrive at some point of time or not. You see, recently in Gujarat or Maharashtra, 2 bridges fell suddenly, causing so many, disruption to traffic, human life loss, and so on. So this is a very important application. So we have done a lot of work with ELCIA, and the very biggest advantage in fiber sensors in health monitoring is in aircrafts. So especially in a fighter aircraft, if I want to put 30 or 40 sensors in a wing, if you put a strain gauge which is 1 centimeter by 1 centimeter or 1 inch by 1 inch, and you put 6 leads per strain gauge, and it is like a trunk of an elephant which is coming out of the aircraft. So this is not which is desirable, because a kilogram of weight saved is kilogram of payload, kilogram of more fuel to fly, and so on. So this is again a view graph from our work. We have put about 30 sensors in ELCIA, and you see all these yellow lines are running the fiber optic sensors which are there. So this is going to be an emerging market, structural health monitoring using fiber sensors. We have done in windmills, we have done accelerometer designs, and so on. So let me take 1 or 2 more minutes. So there are very many strategic applications. So we have built a 500 and 1000 bar pressure transducer for ISRO. You would ask me why there are strain gauge transducers are available, why fiber optic. See, especially if I want to measure pressure inside an hydrogen tank in the liquid propulsion system, you cannot use an electrical sensor that easily because of sparks and so on. Hydrogen is explosive. So we have developed pressure sensors which can be used in a very extreme environmental conditions. And the last one we have done, somebody was talking about UAVs. We have instrumented our DRDO UAV when they were doing the recoil mitigation. We have put our strain sensors to measure strains at various locations. It is actually weaponized UAV, where there is a weapon which fires. And also we have recently developed a sonar for our Navy, which can measure millipascal pressures underwater. So this is for submarine and the other detection. So I would tell you that most of them are TRL level 2, 3. And there are no industries would like to, they have to take it up. If a sonar has to be made commercially, sold to the Navy, we need industries to come in. That is also one of my main reasons to talk about it today. And we have done a lot of work in biomedical domain, be it gait analysis or radial arterial pulse pressure waveform and so on. I'll take 1 more minute. You can play the video. So on top there is a video about, you can play that. So this is our fiber optic sensors. If you want to measure blood pressure when the patient is undergoing a surgery, they put intra-arterial probe, which is invasive. So we were trying to see whether a non-invasive blood pressure measurement and radial arterial pulse pressure waveform can be measured. So this is not an infant, it's a few month, a year-old baby in Indira Gandhi Child Health Institute in Jayanagar. You could see we were able to replace intra-arterial probe with a fiber optic sensor probe. So again, we have done for eye tracking, movement of eyes to detect autism, Alzheimer's and so on. So various biomedical application is there. I will stop with the last slide, environmental sensing, which I did with Honeywell. I think Dr. Yadav was there. We have a patent with Honeywell on this. On carbon dioxide, we have done CO2 sensing, NO2 sensing, various types of gases. And then we have done on mercury. We have done sensors for mercury, cadmium, arsenic, lead, all sorts of. See, you would see this is an integrated platform. I can build one platform for chemical sensing, biochemical sensing, physical sensing, and so on, which is otherwise is not possible. So it's again the last slide. We have done recently on cardiovascular markers and biomarkers. Our idea was whether I can detect all cardiovascular markers simultaneously. C-reactive protein, myoglobin, creatine kinase, troponin I, all can it be done in one shot. We can save a lot of time for the doctors. Within 15-20 minutes, we can do the sensing. So thank you very much. So this is to give an idea of what we have done, what we can do with you in ELCIA, and what we can do with electronic industries in Bangalore. Thank you very much.